Hello, welcome back to my YouTube channel. My name is Prof, and I'm from Udayana University. And today we're back to discuss metal forming process and from the subject of process production. Before we go into the topic, let me tell you my reference. It's a lot from Handbook of Manufacturing Process. Is how product components and materials are made, who made by James G. Bralla, and I got a lot from the web, such as a journal and some YouTube video. So our topic today is contained of three subtopics. The first one is high energy rate forming methods. The second one is straightening. The third one is other forming processes. Okay, let's go to the first topic of the presentation is high energy rate forming methods. The first one we're gonna discuss about explosive forming. Who is explosive can deliver a huge amount of power, such as most explosive detonations are destructive. The power from an explosive charge can be used to manufacture parts. And then an explosive forming process, commonly used for the production of large parts, it is called a standoff system, which is an explosive is placed between the die cavity and the work, a certain distance from the work. Okay, this distance is called the standoff distance. And standoff distance depends on the size of the work. For larger parts, it is usually about half the diameter of the blank. So the explosive itself is also deeply submersed in water. Then upon the detonations, the shock wave travels through the water and delivers great energy to the work, forming it to the die cavity near the instantaneously of the energy rate. Now we're going to the second subtopic of high energy rate forming methods. The second one is combustible gas forming. Okay, the combustible gas forming it is contained with this HERF process. HERF is contain hydrogen, methane, or natural gas mixed with air, oxygen, or ozone. When ignited, provide the pressure wave that form the sheet metal workpiece, and then the speed of the pressure wave is considerably less than the high explosive are used, and its duration is shorter but still measured in milliseconds. Then the pressure wave occurs in the ignited gas rather than in the water or some other medium. So the process is more suited for in-plant operation and for larger productions quantities than high explosive forming. Okay, the third subtopic from high energy rate forming methods is electromagnetic forming. So the electromagnetic forming, as we can see the example, the picture example in the presentation, this electromagnetic forming is used the electromotive force generated by the sudden electromagnetic pulse to form conductive sheet metal workpiece, such as a magnetic coil placed adjacent to the workpiece is subjected to sudden electrical current flow from the discharge of the bank of capacitors. So the magnetic fields produced in the coil induce a secondary current in the workpiece, and there is a repulsive force between the current and the primary current in the coil. So this repulsive force drives the workpiece metal against the die or the other parts and stresses it far beyond its yield point. then there's no contact between the coil and the workpiece, and the magnetic energy will pass through non-conductive materials such as fiber, rubber, plastics, and the operations works best with highly conductive workpiece materials such as copper, brass, and aluminium. So low carbon steel can also be processed in this electromagnetic forming. So the fourth subtopic in this high energy rate forming methods is spark or discharge forming. So spark or discharge forming is both this method and electrohydraulic forming describes below, which is use electrical energy stored in a bank of capacitors to create a shock wave, then which is transferred through a liquid medium, and then in spark discharge forming, then the energy released in the form of a spark across the two electrodes, which is switching circuits instantaneously discharge the energy to the two electrodes. The intense energy emanating from the sparks send a shock wave that forced the workpiece materials against the die walls. As we can see the illustrations in the right from the explanations is the spark or discharge forming, where the external forming coil at the end of the tubbing, the compressor tubbing at the second floor, and that's how they're walk to the die walls. Okay, the fifth subtopic from high energy rate forming methods is electrohydraulic forming, which is this method is very similar to spark discharge forming that we talked about before this, except that the energy is released from an exploding bridge wire connecting two electrodes, which is water transfers the force that forms the workpiece, and then the operation cannot be repeated as easily as spark and discharge forming, but it does provide somewhat greater forming force. This method also most suit to expansion forming of tubular parts. The process is effective, however, if the operation can be performed by more conventional methods, they are usually more economical than the spark discharge forming. Okay, we're heading to the last subtopic in the first topic of high energy rate forming methods, which is pneumatic, mechanical, and pin forming. So this method can be considered as a variation of drop hammer forging, which is compressed gas stored in a pressure tank, or the energy released in the form of gas from combustions of a fuel oxidizer mixture is used to drive a press run to a high velocity, 2 to 10 times that of conventional drop hammers, which is the best application of the process is the forging of parts having thin vertical dimensions and high level of detail. Meanwhile, pin forming, as we can say, is a forming process that does not require any dies and can be performed at room temperature. Of sheet metal is impinged on one surface with a stream of metal shot. The total effect is the generation of general compound convex curve. And then the process is useful when the form required does not involve abrupt curvature changes. As we can see the video illustrations I can play after this explanation. Okay, we're going to the second topic of this presentation, which is straightening. So straightening is basically a metal straightening is a necessary steps in the heat treating process of many components. So due to mechanical deformation and manifestations, of stress during heating and quenching parts often drop beyond acceptable tolerance. Strictness so therefore steel Okay, the second subtopic from the straightening is manual straightening, which is typically the workpiece is clamped at the one end or where there is no deformations. The deformed portion is moved in the opposite direction of the distortions, which is the workpiece is overbent so that it spring back to a straight orientation. The hammer blows or heat sometimes aid in the process. So covers a variety of operations performed with surface plates, levers, vices, anvils, hammers, twisting tools, grooved blocks, and the last one is heating torches. Okay, we're going to the second subtopic of straightening, which is a press straightening. So the press straightening is basically the ram descent and bends the workpiece in the opposite directions far enough so the elastic limit of the material is accessed. If done properly, the workpiece will spring back to straight positions. Indicators and block may be used to find the high points in the deformed areas and to measure the effect of press strokes. So heat may also be applied to the area of deformations. The process works best with materials of Rockwell C3 hardness less than 40. So it uses an arbor or hydraulic press to make the corrective bends. Typically, the deformed workpiece is placed on support blocks in the press bed so that the convex area is on the upward side. As we can see the illustration behind the explanations. I can play after this. Okay, we're going to the fourth subtopic from straightening, which is parallel roll straightening. The parallel roll straightening is as the metal is bent back and forth, which is it is stressed slightly beyond the yield point, exiting from the rollers with a reasonably flat or straight shape. So the operation is rapid since it is continuous and is used on sheet, rod or wire. A series parallel rollers on opposite sides of the workpiece subjects the workpiece to progressively decreasing reverse bends as it passed through the rollers. Okay, we're going to the fourth subtopic from the straightening, which is rotary straightening. So rotary straightening is used two or more rollers with axes at an angle to each other and at an angle to the axis of the part. So one of the rollers has a concave shape while the other is... Okay, we're going to the fifth subtopic of straightening, which is epicyclic straightening. So this workpiece is support on its ends and is rotate. A powered arm attached to the center of the workpiece deflects the center of the workpiece so that it is stressed in all directions beyond its elastic limit. So the powered arm reduces the magnitude of deflection gradually so that the natural axis of the part describe either a circular or elliptical spiral towards the center. So is a property process for straightening axles, tubular drive shaft, and propeller shaft, I-beam, and other sections, and symmetrical forgings from the epicyclic straightening. Okay, we're going to the last subtopic from the second topic, which is straightening. The last subtopic is stretch straightening. So the process is normally limited to workpiece of constant cross section, it is also results in some materials loss since the ends damaged by gripping must be removed. The workpiece is gripped mechanically and stretched in a straight line beyond the yield point. So twist deformation can also be corrected when this is needed. The workpiece is reversed twist when it is stretched. So that's all about stretch strength and the illustration and above the explanation. Okay, we're heading to the last topic of the presentations, which is other forming process. We'll start with the first one is powder metallurgy process, or PM process. So this PM process is typical powder metal parts are rather small and about 3 square inch in cross-sectional area, and is a typical maximum because of the high press force involved. So the process is used for variety of precision mechanical parts, but bearings and other parts with surface that have our metal to metal sliding contact are good applications because the porosity inherent in this part provides space for reservoir of lubricating oil. So almost all metals can be processed by this method. Iron, steel, bronze, copper, brass, nickel alloys, and stainless steel are the most commonly used. So small gears, cams, small levers, sliding blocks, sprocket, and pawls are the other applications. Few further applications are parts made from alloys that are otherwise difficult to machine or fabricate, such as carbide cutting tool, inserts, and tungsten lamp filaments. Is all about powder metallurgy processes. Okay, from the powder and metallurgy processes, there contain a subtopic, and the first one is powder blending and mixing. So the mixing cycle should be short to prevent damage to or work hardening of the powder particle. So drum, double cone, cubical shape, V-shape, and conical mixers with rotating screws are commonly used. The ideal powder for parts making may contain a mixture of powders or different metals or alloys, non-metals, different particle size, lubricant, and binders. So lubricant, stearic acid, lithium stearate, and graphite provide better compressibility and flow characteristic. So benders improve the green strength of the unsistered part. Both benders and lubricant are burned off or volatilized in the sintering process. So blending of these ingredients may take place either wet or dry. So water or other solvent facilitate the mixing and reduce dust. So mixing usually is performed as a batch operations. Like we can see on the both of explanation is the batch operations. So we're heading to the second subtopic of the powder metallurgy processes. The second one is pressing or compacting. So pressing operation forms a green part of sufficient strength for further handling, but not enough strength for functional use. So the die and press motions are summarized in the caption accompanying note, and the note that there is upward force and motion applied from the bottom punch. This is advisable to provide more uniform compactions, overcoming die wall frictions. So the multiple action pressed with multiple motion punch may be used to provide the necessary compactions in all portions of more complex workpiece. In one pressing method, variation the basic die is not fixed. Instead, its motion during the operation provides the equivalent effect of a moving bottom punch. So this variation is called withdrawal die pressing. Okay, we're going to the third subtopic from powder metallurgy processes. The third one is sintering, which is the sintering process is actually has three phases. The first one is burn off, which is remove air and volatiles, benders and lubricants as the temperatures of the compacted part gradually increased. So the volatilized materials must be removed from the furnace atmosphere before the second phase begins. The second phase is a high temperature stage during which the diffusion bonding takes place. This can require a period of minutes or several hours. For iron-based parts, the temperature range from 1850 to 2100 Fahrenheit, or we can convert it to 1010 to 1150 Celsius. Copper, bronze, and brass parts allows somewhat lower temperatures. And the last phase is a cooling phase, which is the lowers the temperatures of the sintered workpiece while maintaining the controlled atmosphere. Okay, we're going to the fourth subtopic from powder metallurgy processes. The fourth one is repressing. So repressing is used to improve the dimensional accuracy of the parts and to improve surface finish, to sharpen certain details, and sometimes to reduce the porosity of the parts, and they may be subject to an additional pressing or calibrating operations. So with some parts, repressing can take place in the same die that was used for compacting. For other parts, separate dies are used, and then the parts are pressed severally enough to cause plastic flow of the material. In addition to the improved dimensions and surface finish, the parts gain some strength from being cold work and densified. So the sintering process results in parts with some shrinkage from the green state as benders and lubricant are removed from the parts. So there's also some inevitable distortions from the thermal expansion and contraction that take place during sintering is going. Okay, we're going to the fifth subtopic from powder metallurgy processes. The fifth one is secondary operations. So secondary operation is part of powder metallurgy parts that can be machined, thread rollered, heat treated, and surface finished after fabrications. So this machining takes place when undercuts, side holes, screw threads, and the other features not visible with the powder metallurgy process are neat. So these techniques are straightforward, but the effect of porosity must be considered. It is usually not recommended to machine bearing surface if impregnate lubricants are planned to be used. So since the machining will tend to close the surface pores of the workpiece, the powder of the secondary operation can be machined. Okay, we're going to the sixth of the subtopic from powder metallurgy processes. The sixth one is powder metal forging, which is in this process the sintered powder metallurgy part becomes a blank for forging. As we talked before, the operation involves more drastic deformation than conventional repressing, and the powder metallurgy part is heat to forging temperature beforehand. Then this process has the advantage that the forging blank can be made to optimum size and shape, then eliminating or greatly reducing wasted materials and permitting the production of more complex forged shapes with reduced necessity for machining after forging. So forgings made from powder and metallurgy blanks can be more precise than conventional forgings. No flash is produced and draft is not necessary. The part is stronger than a conventional repressed powder metallurgy part because it gains the benefit of the improved grain structure that forging provides, and the density is increased to as much as 99% of the process. Okay, after we're discussing about powder and metallurgy forging, that's the last subtopic from the powder metallurgy process. We're now heading to the second of subtopic from the other forming process. The first topic, the electroforming, which is electroforming is a process that utilizes electroplating, that technique to make a form sheet component, whereas in the electroplating, the deposit material is very thin and is left on the surface of the plate workpiece. In electroforming, the deposit material is much thicker and is separate from the substrate after plating to produce a separate part. So there are 3 steps in the process of electroforming. The first one we can see from the left of the illustrations. The first one is preparation of a module. We can see the electrode is coming down, and then the second phase is electroplating of the mandrel to the thickness needed. As we can see the process in the below of a tube. And then the third phase is separation of the electroplate materials from the mandrel. Is the last process or the last phase of the electroforming. Okay, we're going to the last subtopic from other forming process, which is metal injection molding, or we can say MEM. So the MEM process is carried out with low alloy steels, stainless steels, soft magnetic materials, copper, and other non-ferrous metals. It is complex part, can be made with the process to good dimensional tolerance, and a final punch precising operations may be employed when required tolerance are particularly close. This is because of the fine particle size required in the metal powder, less than 20 in diameter, finer than that used for conventional powder metallurgy parts. So the raw materials tends to be expensive. And then is a process we can say somewhere between the standard powder metal forming and injection molding, and as used with many plastic. A mixture of fine metal particles and binders that usually include a thermoplastic, wax, plastic kaisers, and dispersants is heat enough to provide a past-like consistency and is injected under high pressure into a mold cavity. Okay, that's all for my presentation and on my YouTube video. Thanks for watching and see you on the next video. Thank you.